Now that we are done with creation of models, we have looked at different kinds of models, right? We have evaluated models relating to classification. We have looked at the models relating to numerical predictions. We looked at the models which are unsupervised, targeting the cluster analysis, rules, etc. Now, our objective is what are the ways that are available to evaluate the performance of the model? How do I really assess whether this particular model is good enough or I require some kind of improvisation to the model? Now, this is where first let's look at what do we mean by the performance of the model, what kind of models and what kind of performances we are typically looking at, and after that we will focus more and more towards the classification models. So we have built different kinds of classification models. We know decision trees, we know Naves Bayes. We also looked at classification rules or probably neural networks, support vector machines. There are so many such kind of algorithms that we have used for performing the classification of the data. Now, out of all these methods that we have used, how do I really measure which one has done really great? Of course, one method that we have used all across is use the test data, testing it out on the test data and look out for the accuracy on the test data. So whichever one was creating a much higher accuracy on the testing data, we have gone ahead and used that as a better model for our data set. But something more we want to look at, right? We want to extend it to really do a thorough evaluation of the performance of the model. So using the confusion matrix, right, where we talked about the confusion matrices are nothing but it's a table where we have the predicted values on one side. Let's say A, B, C groups are predicted and the actuals are there on the other side, actual A, B, C. So we are trying to talk about how many of them are falling here, how many of them are actually B but have been predicted as A, and so on. So this kind of matrix is what we were calling as confusion matrix. We created the confusion matrices either using the table command or probably the cross table command as well. So we can go ahead doing the same things. We need to look at the various measures of performances that can be used for classification models, and how do I really visualize the graphical ways of representing all these things, and finally what kind of models I can use for estimating the future performance where I don't have information regarding the data for which I'm going to make the prediction. So here we would be taking it with respect to the test data, but yes, so if I have to really look at from the real world perspective, what are the various techniques that are available for me? So we all know for each specific purpose, let's say for classification, we have different algorithms. We have discussed different kinds of algorithms. Each of them has their own advantages, each of them has their own disadvantages. So I need to have some kind of a testing mechanism which is like an exam, right? I need to have an exam out of all these various classification algorithms that I'm using, who did the best. So there should be some kind of a test which clearly bring out who has done, which algorithm has done really better compared to the others. When the same task, same data has been given for learning purpose, and to what extent each of these learning algorithms have really abstracted the learning process, and how many of them, or to what extent they have generalized it, so that given a new data they can really perform the best. So we really need some kind of testing mechanisms to address that particular aspect. Now we have been using this predictive accuracy, right? We have taken 30% of the total data as the test data, and we have been testing this model on the test data, seeing what percentage or what proportion of the total test data is accurately predicted. So the higher is the proportion of the test data accurately predicted, we were relying more and more on that particular model. It's a good way, but of course may not be sufficient measure of performance. So I really want to look at what other kind of performance measures are available. So we see as we move along that there are different kinds of performance methods, different kinds of mechanisms. So to ensure that the various performances reasonably reflect the model's ability. So which are really assessing whether the model has done a good job in terms of being able to predict on the test data or unseen data. Right? It's not overfitted. If I test the same on the training data, there is a possibility of overfitment. But if I'm using it on a test data, then probably this problem of overfitting does not come into picture at all. Now this is where we would like to look at the various methods that are available for classification data. How do I really measure the performance of the various algorithms that I have used for the classification purposes? The first part, which we are all comfortable with, look at the classification accuracy, where I am looking at running it on the test data. I have divided the proportion of the current predictions by the total number of predictions. So if the current, if I am talking about a 300 test data, 270 of them are correctly predicted, 30 of them are wrongly predicted, then the classification accuracy is 270 divided by 300, making it 90%. But what we also need to understand here is, though this classification accuracy is a good measure of performance, but in some cases the 90% may look much weaker, whereas in some cases the 90% itself, like there is something really this model is something really phenomenal. So there is no way I can just look at this 90% and say whether the model has done a good job or not, because the most important reason why I am doing this classification is I have a purpose in mind. So I really want to look at whether my purpose is fully met or not. So I need to have a measure in terms rather than the accuracy in terms of the prediction. I really want to see whether this performance measure, whether this model that I have built is giving me that real intended purpose. Now this is where we are looking at a slightly different measures, different mechanisms of evaluating classifiers. Okay, so from that perspective, we have we can still use the true actual class values. I am comparing the actuals with the predicted values on the testing data. So the predicted class values, always on the testing data we are using the predict, and whatever is the model we are getting the test data. We are computing the predicted values like this. We have the actual class values, and based on that we can also look at the internal prediction probabilities to see whether there is a kind of overlap, midway kind of stuff, right? Because it might be possible that the probabilities are 40% and 60%. So the classifier has put this into the class 1, whereas has not put it into class 0, but the boundary between the two is very, very narrow. So we can very well understand the internal prediction probabilities, which can also be used to evaluate the model performance. If two models make the same number of mistakes, I really want to see the accuracy in the uncertainty part. Right? It's like you don't have too many falling like this. You have many of them to either towards 0 or many of them are towards 100%. So in that case, it's like whatever it has predicted the best. There is no way that this can come into this group or this can come into this group. So the assessment of the uncertainty is done quite effectively. So this could be one more way. Yes, I've taken a test data. On that test data, I am doing the prediction using the model, then compared the actual values with the predicted values, and I'm trying to find out the accuracy of the model. But if two models make the same number of mistakes, I would like to see to what extent the uncertainty is assessed by each of the models. So do we have more probabilities falling in this kind of ranges, or do I have more probabilities falling like this? If they are like this, then the assessment is much appropriate. I call this model as a much more smarter model compared to this particular model. So I want to look at that kind of a model which is extremely confident. So this is what I look at as a measure of extreme confidence rather than this. Because this is, or probably in some cases it is 48%, it is 52%. Just because this has crossed 50, I am assigning it to this particular group rather than to the other one. So I want to look at that particular model which is extremely confident in making a correct prediction, but which is more and more timid in face of a doubt. So this is where when the doubt is coming out, it is not able to do a proper calculation, but wherever in majority of the cases wherever it has done a correct prediction, it's a very extremely confident in doing that kind of a prediction. So we have to understand that looking at confidence in terms of prediction and the caution that it has taken in terms of giving the right versus wrong predictions is a very, very interesting and important part of the model evaluation process. We need to be understanding that particular aspect very well. So we know that we can get the probabilities for almost all the processes that we have used. So if I am talking about the decision trees and rules, I can very well use type equal to prob and get the probabilities of each of the groups. Right? So let's do one thing. Let's take up a small data set. Let's use this decision rules. The right decision trees we'll use, and we'll try to quickly do that particular process and try to use the results of that particular process so that we can go ahead in terms of executing the various other methods to come out with evaluating the performance of this classification model, right? So let me bring in the R. Okay, so I've stored this diabetes related data. I'm pulling out this diabetes related data into my R workspace now. So if I look at the dim of diabetes, it's having 600 rows, 7 columns. So I could also look at the summary of diabetes. It says that okay, it's having 392 negatives, 208 positives. Age, these are the numbers. Of course, I have a few NAs in the model. In the glucose, pressure and mass columns, I have a few NAs. So it's better that I omit those rows which have NAs. So what I'll do is diabetes. I'll do an NA dot omit so that I'll remove all those columns or all those rows as such. So let's say I'm talking about NA dot omit diabetes. Now let me talk about dim of diabetes, which says now there are only 564 rows and 7 columns. Fair enough. Let's go ahead with this set itself. 564 rows, 7 columns, right? And now if I am quickly looking at the summary of this, okay, so this is the summary. We have glucose right from 44 to 198, right? The pressure is from 24 to 122, mass is 18 to 67. So we have different kinds of values, and finally we have negatives 372 negatives and positives are around 192. So this is the data that we have, right? So what I would like to look at is I'll take a 70% of it. So I'm first setting a seed at 1000. So 70% of 564, 564 into 0.7, if I look at it's around 395. So I'll take 395 as my training data. So I'll say train sample 1 to 564. 1 to 564, I'm pulling out 395 observations where the replace equal to false. I am not repeating the things. So this is what is my train. So I'll take my train data, which happens to be the subset of diabetes, which will contain these rows only. So it will contain the rows that are present as a part of the train, and it will contain all the columns. Okay, so that's my train data. I also have my test data, which is again a subset of diabetes minus train comma space. Okay, this is my train data, this is my test data. So now I want to build a classification tree model or a decision tree model. So we'll use the C 5.0 algorithm for that. Alright. So let me take library C50. So I have taken the library C50 because I am building the C 5.0 decision tree for this particular model on the training data. And so I'll use C 5.0 function. Okay, so I'm taking the C 5. So we'll create it as a model, right? Model 1, let me call it. So I'll take it as C 5.0, wherein first I need to give my training data. So I'll call it as train data, and the class. The class is something which I have to give it as a vector. So here the train data, actually I should segregate it without containing the diabetes. So let me take all the rows, only 1 to 6 columns, or minus 7, whatever it is. So I am giving this as the train data. So the whole training data that is present I am giving out here. Then I have to give my class for the training data, the class variable. So this is where I can very well take it as train data $diabetes, which will become the class for the training data. If at all I have to give any kind of trials, especially for the boosting and all, I can very well give it. Otherwise, I can simply finish up the model. So the model is created for me. The model 1 got created. And so now if I look at just typing the model 1, it is saying that it's a classification tree where the number of samples is 395, 6 predictors have been used. The size of the tree is 17. And if I am looking at the summary of this particular tree, summary of model 1, I am getting it more like this. Okay, the classification came like this: glucose greater than 142. So within that, I have pregnant greater than 6. So there are 36 observations, out of which 5 are 36 are so they are all positive. The decision is positive because 36 of them are coming under the positive segment. Only 5 of them are wrongly classified. Similarly, pregnant less than or equal to 6, then again we are looking at greater than 5. The decision is coming out to be negative. So this is how the tree has actually read through the whole thing, right? And finally, you could see the glucose is the major usage across. Then came out with the mass, then pregnant, pedigree, age and pressure. Probably age, pressure are looking at much lesser kind of contributors, whereas glucose and mass are contributing on the slightly higher side. And even if you look at the errors, it is working out to be around 60. 31 plus 29 are the wrong classifications. So 60, which means 15.2% is coming out to be the error rate when you have done this exercise on the training data. But we say that we should execute the same on the testing data. So we'll call P1, wherein I'm trying to predict using this model 1 on my test data, where I'm considering all the rows and columns only 1 to 6, and I'm doing the prediction on this test data, right? So I got my predicted values there. Now this is where if you look at the P1, I've got the predicted values out here, right? So by using these predicted values out here, I could very well compare. I could make a table, right? I can very well make a table of P1, which are the predicted values, and the actual values is nothing but test data dollar test data dollar diabetes. So this is becoming a table, and if required I can even create drop dot table on the top of it, so that I'll get all these things in the percentage form. I'll get all these in the percentage form. So it shows that 0.12 and 0.13. So almost 25% is the error rate, right? 0.12 here, 0.13 here. So overall 25% is the error rate, 25.4, whereas around 74.6% looks like the accuracy of the model when I am doing this testing on the test data. But the same P1, right, instead of considering, okay, let me call P1 underscore prob, where I am considering the probabilities. I could have simply taken, along with this I will type equal to prob. By doing this typing, I'll get the probabilities associated with each of the classes. P1 underscore prob, now if you look at, for all of them, it will show me what is the probability that it will fall into a negative, what is the probability that it will fall into a positive. So we are getting some kind of prob values which indicate the probability of the data falling into a negative group versus a positive group. Now we would also be assessing those probabilities to understand how confident the model was in terms of classifying it into a negative group versus a positive group. So the first thing, when we are measuring the performance for classification, use a data frame containing the predicted class. So I require a data frame which contains the predicted class values, the actual class values, and the estimated probability. So I'll have a quick data frame which will have the predicted class values, the actual class values. Predicted class values are coming out from the prediction, actual class values, and even the estimated probability of at least one of them. So let me call it as DF, wherein I'll create the data frame. I'll create the data dot frame of P1, P1, okay, which is the predicted class value, test data dollar diabetes, which is the actual class value, and I am also giving P1 underscore prob dollar positive, right? So I'm more interested in positive, so let me take P1 underscore prob dollar positive. So using these I have created a data frame. Okay. So let me convert all of them as dot data frame otherwise. Or let me do as dot data frame, and let me do a C bind of all these things. P1 underscore prob Alright, let me just check the class of P1 factor. Then let me look at class of test data dollar diabetes. It is also a factor. So class of P1 underscore prob dollar pos, P1 underscore prob. Okay, this is where the problem is coming out. Instead of saying dollar prob, let me call it as column number 2. Okay, so this is numeric. So when I'm doing a binding, let me go ahead in terms of, instead of simply putting P1 underscore prob, let me simply take it as comma 2. Let me see now if this works. Yes. So now the DF is worked. So let me take the DF. So this is what is coming out as a part of DF. The probability that it is going into the class. So we have got the P1. We have got this is the predicted. This is the actual, and the probability that this particular observation is going into positive, right? Where the diabetes is positive. So 1 means negative, 2 means positive, and the accuracy with respect to the prediction. So we are taking this data frame, we'll use it for various purposes at a later point in time. So this is how we are predicting the actuals versus the predicted, right? So if the estimated probabilities fall on the extremes, then it can be inferred that the model was very confident. Now look at 65, these are all not on the extremes. 28, not on the extremes. 65, 64. So these means they are not on the extremes. 65, 35s, Whereas a lot of these things, 8, right, 8. So these things does not mean that it is on the extremes, whereas 65s very clearly indicate that they are on the extreme. 85, 28s are there, 90 is the extreme, but 28 need not be the extreme. So the more and more the values are towards 0 or towards 1, we talk about the goodness of fit of the model. It's very confident in terms of doing the prediction of the classes, but more and more it's away from 0, away from 1, more closer to the middles, then we can say that the confidence levels are much lesser. So we are creating a confusion matrices, which is a table which is categorizing the predictions according to whether they match the actual values or not. Right? We know that. So any number of classes we can create a matrix. When the predicted values, so I can very well take a table wherein I am collecting P1. I am also taking the test data $diabetes. So these are the actuals. So this is what we call as a confusion matrix. When the predicted value is same as the actual value, it's a correct classification. So generally the ones on the diagonals are correctly classified. So we have 126 observations correctly classified, whereas 43 observations are wrongly classified. So 126 divided by 126 plus 43. So these many are, this is the accuracy rate. So almost 74.5% is the accuracy rate of this particular model. Off diagonal matrix cells which are not on the diagonal indicate that the predicted value is different from the actual value. So here the predicted value was this person is positive with diabetes, whereas the actual value is he is negative with diabetes. The same logic here, the model has predicted this person will be negative to diabetes, whereas they are positive to diabetes in reality. So the performance measure for classification models are based on the counts of predictions that are falling on the diagonal versus off the diagonal. Now we have to finally understand out of this where to improvise to take the performances to the next level. I need to have an understanding of what is my positive class. So what is my class of interest? I want to know whether a person is going to get diabetes or not. So the positive for diabetes, I will take it as a positive class for all my future stuff. So negative for diabetes is taken as negative classes out here. So this is how we have to understand now the four classifications. So let's say positive is what is the class of interest for me, whether a person will develop diabetes or not. So that's the reason I'm looking at positive being a class of interest. So that's where I have considered being positive as a positive class for me. So we have four different things in a confusion matrix. True positive. True positive is this one. Right? If I'm looking at true positive, 43 elements are truly positive. So my model has correctly classified as the class of interest. So my model has predicted that this person will develop diabetes, and in fact they had diabetes. So 43 are correctly predicted, and that's why I'm classifying it as true positive. Similarly, I also have true negatives, which means these 83. So 83 people my model has predicted they will not develop, they are negative for diabetes, and even in reality they were negative for diabetes. So the negatives were predicted correctly. So that's the reason this is true negative 83. Then false positive. False positive is nothing but I have incorrectly classified as positive. They are actually negative. They are actually negative, but I have given them as positives. I have predicted them as positives. So these ones I have predicted as positive, but they are actually negatives. These ones I am calling them as false positives. I have falsely predicted them as positive, incorrectly classified as positive. There are 21 of them. And false negatives is incorrectly classified as negative. They are actually positive, but I have incorrectly classified them as negative. So we really need to have a good understanding of these four, because the various performance measures that we are going to come up with, they are more focused on trying to improvise or trying to make computations based on these four specific values. So how many false positives, false negatives are there? How many true positives, true negatives are there? We are going to look at all these aspects. So from the confusion matrices, right, once we have created this false positives, false negatives, the prediction accuracy is nothing but the success rate, wherein I am looking at true positive plus true negative. So we have already taken true positive is 43, true negative is 83, divided by all of them, which is what has given me 74.55%. And error rate comes out as 1 minus of this. So 1 minus of 74.55% is giving me around 25.44%. So I am getting my error rate from that particular mod. Or I could have used, instead of a simple table, I can very well use a library of G models where I can use the cross table function. Right, cross table, wherein I am considering the actuals, which is the test data dollar diabetes, and I am also considering the actuals, which is P1. So the cross table actually contains a slightly more details, as we know. Right now you could see the negative, positive. These are my predicted values. These are my actuals. The first one is N, 83, 21, 22, 43. Chi-square contribution. Okay, right now we can ignore the chi-square contribution. N to the row total. So the total as per the row total, so almost 80% of the total negatives, whatever are the total negatives 104, 83 of them are correctly classified. So almost 80% of the total negatives are correctly classified. Only 20% of the total negatives are wrongly classified. But when it comes to the positives, only 33% of them are wrongly classified, whereas 66% of them are correctly classified. So similarly, I am taking it with respect to the column total 83 divided by 105, saying out of those which I have predicted as negative, the model has predicted 105 as negative. Out of them, 79% are accurate, only 21% of them have a problem. But for 64 of them which the model has predicted positive for diabetes, 67% of them are correct, 32.8% of them are wrong. And overall, these are the percentages across. So that's how my cross table can give me slightly more details compared to the typical table function. Now, Going beyond the accuracy computation, the error rate, which we have been doing even in the other sessions as well, we are looking at a few other performance measures explicitly targeted towards this purpose, looking at these four elements: the true positives, true negatives, false positives, and false negatives. So we are talking about different kinds of measures for each of these. Here we would be using a package called Carrot, right, which is nothing but classification and regression training. We'll use this particular package which has so many performance measures that are built into it for classification model. Even for regression models, it has quite a good number of measures. So we can very well install this particular package Carrot, and after that we can really start going ahead with the assessment of the various computer performance measures. So Carrot as a package has a good number of tools for preparing, training, evaluating, visualizing the various machine learning models. So we can very well create a confusion matrix, and it can really simplify our overall understanding now. So let's install the Carrot package first. I think it's already installed on my system, so I'm just loading it. Yes, the package is already there. So I've loaded the Carrot package. Then I have to give the confusion matrix is something that I'm going to create. Let me just see what it requires. Confusion matrix. If you look at this confusion matrix, it is asking for a data which is a factor of predicted classes, a factor of classes to be used as true results. So the reference is the actuals, which are trues, and I should also give what is the meaning of positive, an optional character string for factor levels that correspond to a positive result. If there are only two levels, the first level will be used as positive if I did not give anything. But I have to really specify what is the meaning of positive. So I have to first give the data, which is the predicted. Then I have to give the reference, which are the actuals. And I also need to give that particular column, which is typically called as treated as positive, which is the class of interest. So let me create a confusion matrix. I'm taking a confusion matrix. My predicted value is P1. My actual is test data dollar diabetes, and the positive is POS. POS is what I'm treating as positive. And based on that, it should be creating the confusion matrix for me. This is what is created as the confusion matrix. So some of the things which we have already computed earlier, the accuracy has come out to 74.56%, right? This is the confusion matrix that it has created. So the 95% confidence interval is around 67.3 to 80%. So that's the kind of accuracy that I can get even if I am actually changing the samples, etc. So my typical accuracy can range anywhere between 67.3% to 80.93%. That is what is being said about this model. Then we have a no information rate of 61. The p-value of accuracy greater than the no information rate is much lesser. The Kappa statistic, which is what we are going to deal with now, is around 46%. So there are a few other calculations. All these things we are going to look at what each of them are going to mean for us. What is sensitivity? What is specificity? What is the detection rate? What is the balanced accuracy? A few things. The positive class, we have taken it as POS. So we will look at each of these things. Now, the improvisation is, first let's look at the kappa statistic. So here what it does is it is adjusting the accuracy. Now we have got the accuracy in this case as 74.5%, right? And we have said that this is a very high accuracy. But now what the kappa statistic is doing is it is adjusting this accuracy. It says no, 74.5 is a false accuracy for you, because it is actually accounting for the possibility of correct prediction by chance alone. So there is something that just by chance I can get this accuracy. The allotment, okay, this may not be because of the model, this could be purely because of chance, right? So that part of it, it is simply omitting it, adjusting it, and based on that it is trying to compute the accuracy of the model. So this would be a much better measure to assess the goodness of the model. So it can range anywhere between 0 to 1. The values are very close to 1. It means that the model is excellent. If it is very close to 0, then the model is a poor fit. Now if you see in our case, before we compute it, we got the kappa as only 46%. So it's only an average, moderate kind of a fitment. The model is not that excellent. So probably if you get a chance, you try to go ahead with some of the model and see if it can really improvise your performance, right? So that is what is typically that can be understood out here. The way the kappa is computed is the proportion of the actuals PRA, proportion of the expected, agreement between the classifier and the true values. So we are taking this, I'll explain it with our example itself. So the way the kappa is computed is probability of A minus probability of E. Probability of E is the probability that the allotment is happening just with chance. So we will see how we will compute them. So probability of A minus probability of E divided by 1 minus probability of E. That is how the kappa is typically computed. So we will see how we can compute that kappa. Right, let's compute the kappa for our data. So the probability of A, when we are looking at the probability of A, I'm looking at the total correct classifiers, the actual classifiers out here, because it's an actual agreement between the classifier and the true values. So if I really want the probability of A, so I'll call it as PR underscore A. From my matrix, PR underscore A is nothing but this 49% is correctly classified, and along with this even this 25.4% is also correctly classified. So the PR of A, we all know it's around 75% something, 74.5% is the probability of A. But if I'm looking at the probability of E, I'm looking at it is the probability of it being under chance alone. So for that what we will do is we will do negative probability of total negative, predicted negative multiplied by actual negative, plus predicted positive multiplied by actual positive. So this is what we call as, so which is nothing but the probability of predicted. So the if they are completely independent, this negative and this negative, this positive and this positive are completely independent, then the probability of E, PR underscore E would have come out as 0.621, which is the probability of predicted negatives, multiplied by probability of actual negatives, plus probability of predicted positive multiplied by the probability of actual positives. Probability of actual positives. So it comes out that PR underscore E comes out as almost, so there is a 52% chance, just with chance alone I can get the allotments to be done across the classes. So that is what is coming out as the PR of E. Now I have all these values. I can very well calculate my kappa, which is nothing but PR of A minus PR of E divided by 1 minus of PR of E. That is what is being coming out as the kappa calculation. So this says, in this case, it is working out as the K is coming out as almost 46%. So we got more or less a similar kind of a result, right? Because I think some rounding offs are happening. So we have got the kappa to be more or less to be the same. Almost 46% is coming out to be our kappa statistic. So if any other model is having a slightly higher value of kappa, that would be more and more preferable compared to this particular model. So it has to agree with the confusion matrix, whatever the kappa that we have computed, it has to be more or less in line with the confusion matrix that we have created. So the higher is the kappa value, the higher is the goodness of fit of this particular model. Alright. So this is the way we can compute the kappa statistic. But of course, there are quite a few other ways in which I can directly compute the kappa values. I have a package called BCD, Visualizing Categorical Data. So there I can simply give a confusion matrix of predicted and actual values, and it can give me the kappa statistic directly. So if we see, let me load this library VCD. If it's not there, I'll install it, but I think it should be there. Okay, so it is installed the VCD package. Then I'm using the kappa function, wherein I'm taking the table. First I'm giving my actuals, test data dollar diabetes, and I'm also giving my predicted, which is P1. So it will compute the kappa statistic for me. So here also you could see the kappa statistic is coming out to 46.09, both in case of weighted as well as unweighted. So we would generally look at the unweighted value of kappa, right? Especially when there are more than two categories, then there is a slight difference in the way the unweighted and the weighted results will come. But when there are only two categories, then both of them will give me the same result. So even through this mechanism I can get the kappa. The only thing is I have to load the VCD package. Otherwise, there is one more way in which I can get the kappa using the kappa 2 function, especially which is present in inter-rater reliability package, IRR package. So let me install the IRR package. So inter-rater reliability package, even there I can get my kappa value. So let me load this IRR. Okay, so my IRR is loaded, so I can very well use the Kappa. So if you look at the Kappa 2 in this iterator reliability package, it calculates the Cohen's Kappa and weighted Kappa as an index of inter-rater agreement between the two raters on categorical. So it takes them as two different raters. So you could very well specify the ratings, right? I could very well give the ratings, which is an n by 2 matrix or a data frame. So I have to give two. One is the predicted and the other one is the actual. Both of them, it should be in the form of a matrix or it should be in the form of a data frame. So now that I have already computed DF, right? Probably if you look at the class of DF, it is a data frame, right? We have created the data frame, predicted values, actual class value, and the probability. So if you look at the head of DF, it is this one. So we have the first is the predicted, second is the actual. So Kappa 2 I'll give the ratings, but the way we are using is this is actually for two different raters. If they have given two different ratings, we can very well understand what is the level of association between them by going ahead with this kind of by looking at this kind of an analysis on the Kappa part. So let's look at this Kappa 2. So wherein I'm looking at DF, I'm taking all the rows, but I'm considering only 1 to 2 columns. So those are the data frames that I'm giving per Kappa. So this is how I'm getting my Kappa value. There are 169 different subjects. So 169 is my test data. The Kappa is coming out to 0.461. Again the same logic. So the same Kappa that we have got even in the earlier scenarios. So whichever is the option that you are comfortable with, you can very well go ahead and. So the Kappa is one kind of a measure of the accuracy, especially if we are talking about a categorical data classification. Then we'll move on to another measure, which is the sensitivity versus the specificity. So whenever we are doing a classification, we have to really balance between being overly conservative. When you say overly conservative, categorize all of them to positive, saying they are all diabetes positive. Or I can go overly aggressive, saying none of them is positive for diabetes, all of them are negative. So I can make mistakes which are false positives, or I can make mistakes which are false negatives. So I have to really strike a balance between what proportion of mistakes I am creating under the false positives and what proportions under false negatives. This is what we differentiate between being overly conservative versus overly aggressive in the decision making process. Now, understanding that is coming through a mechanism called sensitivity, which is talking about the true positive rate. So in reality, what is the proportion of truths? Which means it includes true positive versus false negative. They are actually positive, but I have predicted them as negatives. So out of the total positives, right, if you look at the table again, if you look at the table, these are my predictions. These are the total positive ones, right? Out of them, I have predicted these many as correctly positive, but this 21 of them, I have predicted them as negative. No, my prediction negative, this is the one. They are actually positives, right? If you look at false negative, I have predicted it as negative, but they are actually positive. So overall there are 65 positives in reality, out of which 43 of them I have predicted as positive correctly. 22 of them I did not predict correctly. 22 of them I said negative, whereas in reality they were positive. Right? So I can very well compute the sensitivity as total positive divided by total positive plus false negative. If you really look at, this is nothing but proportion of the column total. Right? The proportion of the column total is coming out, are proportions of the row total. So you could see 33.8% is wrongly classified, 66.2% is correctly classified. So this 66.2% is what we are calling as the sensitivity. So if you see here the sensitivity that it has computed 66.15%, which is nothing but this 66.2. So that's the way we compute the sensitivity. Total positive divided by total positive plus false negative. And at the same time we are talking about specificity, where I am looking at the true negative. So actually they are negatives. So this is what is actually they are negatives. But I have predicted in some cases that they are positives. So the specificity again is the proportion of this row total. 79.8% is done correctly. 20.2% is done wrongly. So typically it will give me that the specificity is 79.8%. If you look at it here, specificity comes out to 79.8. So this is where we are looking at true positives versus the true negatives. So in true positive, we are saying proportion of the positive examples that were correctly classified, that is sensitivity. Proportion of the negative examples that were correctly classified comes out to specificity. I can use the function sensitivity and specificity directly from this caret package, where I give the predicted and the actuals if required from the caret. I have the function sensitivity, right? Sensitivity of the predicted value P1, the actual value test data $diabetes, and I am also have to give what is the meaning of positive here. Positive equal to pos. So the sensitivity is coming out to 66.15. The same logic, I have another function called specificity. Specificity, which is okay, specificity of the other way, right? Negative. So specificity I can give it with respect to the negative. The negative is NEG. Oh, sorry, I have to give it not as positive, negative. Specificity takes negative as the input. So it's almost 79.8%. The sensitivity takes positive as the input. The specificity takes negative as the input. So these also range between 0 to 1. Values very close to 1 are more and more desirable. So what we do is we try out all the different kinds of models, right? We could try KNN algorithm, we could try neural networks, whatever. We can make the changes to the model, and different models are tested until I get much higher and higher levels of specificity as well as the sensitivity value. So this is one more measure of assessing the performance of the classification models. Then there is another dimension for the assessment, which is called as precision versus a recall. So even these are a kind of indication of how good the classification models are. How well my model is able to do the classification of the data more or less accurately. Or is it that the predictions that I am creating, they are diluted by the meaningless noise? So The precision talks about the positive predicted values. So we are only looking at this column here. Now if you see, this is just a different way of looking at the same table. So here, while specificity and uh, sensitivity, they have looked at the actual negatives and actual positives, true positives and true negatives. True positives being evaluated from the perspective of sensitivity, true negatives from the perspective of specificity. Precision and recall look at the predicted positives versus the predicted negatives. So the predicted positives, positive predicted value is the meaning of precision. Proportion of positive examples that are truly positive. So here if you see, there are 64 positive predictions that it has done. Out of them, 43 of them are truly positive. So which is what says almost 67.2% is truly positive, 32.8% is not positive. So when a model predicts the positive class, how often it is correct? The higher it is, the more trustworthy it is. So in this case, this number worked out to 67.2%. Whereas recall is saying measure of how complete the results are. Right? It is looking at what is the level of completeness of the result. It's more and more similar to the sensitivity itself. So we have totally positives out here. It's looking like this. So out of which, what is the accuracy? So out of this, again it is saying 66.2% is the accuracy. True positives divided by true positive plus false negative. False negative is I have predicted as negative, my model has predicted as negative, whether they are actually positive. So the row totals wise, if I am looking at, it's around 66.2%. So the precision is 67.2%, recall is 66.2%. Measure of how complete the results are. It looks like formula wise it's same as sensitivity, wherein I am looking at the number of true positives over the total number of positives altogether. So a high recall, which means I will get a much higher percentage for the recall values, which is also an indication that all the positives are correctly classified. I could have very well used positive predicted value, right? I can very well go ahead with computations of the precision and the recall through that mechanism, and I can also use based on the positive predicted value. I can very well get, so I could use pos spread value from the carrot package. Again I have to give my prediction P1, the actual is test data $diabetes, and I have to give my positive is POS. So from there it works out that it is 67.185. So which is nothing but, this is where I've got my 67.185, which is 67.2 out here, which is nothing but the precision. So this is how we can do different kinds of calculations. So it's very much difficult to build a model which is high on precision as well as high on recall. So I have to really set some kind of cutoffs for both the precision as well as recall. Try out different combination of models to see whether my model is meeting the cutoffs both for precision as well as for recall. And I would be choosing that particular model which has crossed the cutoffs for both the precision as well as the recall measures. Then comes the F measure, which is actually a combination of precision and recall, which is nothing but 2 into precision into recall divided by recall plus precision, which is nothing but the harmonic mean between the precision and the recall. So 2 into the precision is nothing but TP by TP plus FP, and I also have recall, which is nothing but TP by TP plus FN. So this is 2 into precision plus recall. Recall plus precision is nothing but TP by TP plus FP plus TP by TP plus FN. So if you try solving this whole thing, it works out as 2 into TP by 2 into TP plus FP plus FN. So which the other way I could very well take 2 into precision into recall by recall plus precision. So which works out as F is nothing but 2 into, this is my precision, into recall is nothing but the sensitivity value, 2 into precision into recall divided by precision plus recall. Here you should get more or less the same because both of them are almost similar, almost equal. So F value works out to 66.67%, right? Which is 66.67% is a measure of the F measure for this particular data set. So the higher is the F, the more better is the classification accuracy. So it's as good as we have combined both of them, and I can use this F measure for comparing two models. Right, the model which is having the higher F measure would be the choice for me. So that's where we could use all these different kinds of mechanisms, which involves the true positives, the false positives, true negatives, and false negatives for doing lots of computations, finally assessing the goodness of fit of the models. Then the next aspect that I want to look at in this context is how do I really visualize the performance trade-offs? So when we are doing the visualization or a graphical display, it is helpful for understanding how the performance of various machine learning algorithms vary from situation to situation. So I'm looking at different kinds of learning algorithms, right? I'm trying to compare different kinds of learning algorithms in one single chart. So for that, it was better that we use ROCR package. ROC is nothing but receiver operating characteristic. We would use a lot in binary classification models. We call them as ROC curves. So we are using ROCR package, wherein we would like to look at different kinds of visualizations of the performing statistics exclusively for the classification models. So we have to give to the ROCR package, the inputs that I need to give are the class values predicted. So we got P1 in our example. So the P1 is the predicted class value. And I also need to give the estimated probability of the positive class. So we have already taken that as a part of the data frame. So I will give the predicted probability, estimated probability of the predicted class. So by taking these two things, it will create a prediction object using the prediction as a function. So I have to give these two as the inputs. Let me start the process. Let me install the package ROCR, right? That makes things easier for us to understand. So I am taking this ROCR package. So I'm doing a prediction object. I'm creating a prediction object. If you see what is being happening as a part of this prediction. Oh, I have to load first of all. Yeah. Let me load this library ROCR. Then I'll use this prediction. If I look at this prediction, every classifier evaluation using ROCR starts with creating a prediction object. I have to create a prediction object. So wherein it will take the prediction. Predictions are nothing but it's a vector or it's a matrix or a list or data frame containing the prediction. So here I have to give both. When I am talking about the predictions out here, I am giving both the probability. So I am creating a prediction object by simply taking the actual predictions and the labels wise. I have to first take the prediction object wherein I am taking the probability. The first thing I will consider is prediction is I'll take the probability, and labels wise I'll take the class. So with these both the things, I am creating a prediction object. So let me give the prediction object first. So let me call it as pred. I am creating a prediction object which will contain the predictions as a field, which is nothing but I am taking the probability. So let me take the df and the third column in the df, right? I'm looking at the estimated probabilities is something that I have to give. So I'll take the third column of the df, which is containing the estimated probabilities. So that is what I am taking as the predictions, and as labels I can always take the actual labels. The actual labels are nothing but test data $diabetes. So considering these two, I am creating a prediction object. So this spread is nothing but a prediction object. Now if you look at the spread, it has actually created so many things. So it has taken, first of all, it's an object of the class prediction. So these are your predicted probabilities. These are the labels. So it has done some kind of cutoffs for the various slots. It has done the cutoff for various slots. Then from there it has looked at the false positives, true negatives, false negatives, and overall it has come out with number of positives, number of negatives, which we have got there, number of positives predicted and n dot negative predicted. So this is how this whole classification has come out. So because it has done the cutout, because we will get an ROCR curve now. So this is the first step. I have created a prediction object using this spread. And we will also look at a performance object after this, wherein it will take the prediction object as the input and it comes out with a measure of performance on it. And once that performance is created, once that performance function is used on the prediction object, we will try to visualize it using the plot function. But before going there, let's try to understand what is this ROC curve. If you see here, it is a kind of a trade-off between the true positives. So this is the graph where we are talking about true positives on y-axis while avoiding the false positives. Means I am creating something as I have predicted something as positive, but actually it's not positive, it is negative. So that is what are called as false negatives. So I want to minimize the false negatives to whatever extent possible while increasing the true positives. So this is what is the graph that we are plotting. We have false positives on the x-axis, the true positives on the y-axis. The curves are defined on the plot. The proportion of the true positives out of the total which we look at, what is the proportion of the true positives on the vertical axis and proportion of the false positives on the horizontal axis. So we have the false positives, okay, as the false positive is going out to 0%, what are the true positives? As the false positives went to 1%, 2%, 10%, 100%, as the false positives became closer and closer to 100%, what is the extent of the true positives that are coming up? So false positive is nothing but 1 minus the specificity, whereas the true positives is talking about the sensitivity, right? So it is known as the sensitivity specificity plot because the true positive is nothing but the sensitivity, false positive is nothing but 1 minus the specificity part. So that's where ROC curve is also called as a sensitivity versus specificity kind of a plot. So the true positive rate at different kinds of varying false positive thresholds. So I keep changing the false positives. I keep setting different thresholds for false positives, and based on that I will see what is the true positive rate. The simple way this whole process is done is, so we have got the predictions, we have got the prediction probabilities of the positive class. What we typically do is we sort it in the descending order. So if I look at the prediction probabilities of the positive class, right, let me look at the DF. If you look at the DF, we'll look at only few of them. So these are the prediction probabilities of the class, right? Now this is sorted in the descending order. So once it is sorted in the descending order, beginning at the origin, each prediction's impact. So we are doing the first prediction, second prediction. Let me do this sorting on the descending order. So we are talking about DF, or let me take order DF dollar V3. So this is the order. Probably I have to take the reverse order to get the descending order. I have taken the reverse to get the descending order. So from there I can very well set DF of, I'll take these rows. I'll take these rows and I'll simply take all the columns. So this is how my data got sorted. If you see here, right, so 903s are at the beginning. Okay, so these are my predicted values, these are the actuals, and this is the probability going into each of these class. So beginning at the origin, each prediction's impact on the true positive rate and false positive rates. So we are trying to compute the true positive, each prediction's impact on the true positive. So here it is true positive. So I have predicted this as positive, but it is actually false. Here again, predicted positive, actual positive, predicted positive, actual positive. So this is how I am looking at the true positive versus the false positive, resulting in a curve that is going vertically. So if it goes more and more vertical, which means the more number of true predictives, true positives coming, very less number of false positives. Then what is happening is my false positive, for a very small value of false positive, the true positive has already gone up drastically. So I'm seeing that the true positives keep going up and up, but the false positives don't start increasing at all. Now it is in this case I get a kind of a more and more vertical kind of movement. So the more vertical the movement is, it goes for a correct prediction. The more horizontal the movement is, it goes for a much stronger incorrect kind of prediction. So if you see this curve, there is one diagonal that we are talking of. Okay, when the false positives reach 20%, true positives are also reaching 20%. False positives are 40%, true positives are also approximately 40%. So in that case, the model is not doing anything good. So there is no proper predicted values at all. It's more and more random. In that case, I see a 45-degree line. So the diagonal line coming from the bottom left to the top right is talking about a classifier with no predicted values. Because the true positives and false positives, both of them are predicted at the same rate. So it's almost a random. It could be either true positive or false positive, true or false, the prediction. So it's almost like a gamble. So the classifier is not able to really discriminate between whether it is correct or wrong. In that case, the curve comes more and more as a 45-degree line. And what we could say is, if our actual curve is somewhere close to this line, we say that our prediction is nowhere closer to good. But we will try to compare all the models with respect to that particular line. How close is it? How close is the actual curve to that particular straight line? The more closer it is, the poorer it is in terms of doing the predictions. The more farther away it is from that 45-degree line, I can really assess that it is doing a good job in terms of doing correct prediction. So the ROC curves which are coming close and close to that line say that the model has not done a good job. And if it is a perfect classifier, see, if you see, if the false negative, false positive is close to 0%, still by that time itself, I could see that the true positives have gone close to 100%, which is an indication that it is very vertical. So very limited amount of true positives, false positives. So the model has been able to do a perfect classification process. So almost 100% true, 0% false positive itself. So that kind of a model is called as a perfect positive kind of a classifier. So our model is able to correctly identify all true positives before it incorrectly classifies any kind of a negative result. So all positives are coming out perfectly first, and then only the negatives start coming out. So most real world classifiers, if you see, they should be somewhere in between the two. Probably either like this test classifier, or some of them could be like this, some of them could be like this, some of them could be even like this, but they are the kind of curves that can come out across. The more and more closer to one, they are doing a good job in terms of classification. The more they are away from one, their classification is more and more poorer. So the close to the curve, closer the curve is to the perfect classifier, I say the model is doing a good job. It is able to identify the positive values quite comfortably. But at the same time, we are interested in looking at the area under the curve. Right now, we are looking at this is the ROC curve. We are trying to see what is the area under the curve. So if the curve is more like this, then the area under the curve is all this, between the curve and this line. So the area under the curve tells me the higher is the area, the better it is closer to a perfect classifier. So this area under the curve should range somewhere from 0.5 For a perfect classifier with no prediction values, the value will be 0.5, but for classifiers with perfect, then the value will be zero point 0.1. So we would generally be seeing that if the number is somewhere between 0.9 and 1, we'll call it outstanding. Excellent is for 0.8 to 0.9. These are just a kind of quick benchmarks, but they are just for a ballpark kind of estimate. There's nothing called the best way of computing the or assessing when is the ROC curve really good, when is the model really doing a great judgment altogether. So true positives, false positives. So once we have this data, I have to really give I can very well find out the performances. Right, let me look at the performances of the model. So let me create a function called performance. For that, let me assess what this performance is doing. All kind of predictor evaluations are performed using this function. The first input to it is a prediction object. We have already created a prediction object called pred. Then I have to give a measure, performance measure to use for the evaluation. So if you look at the different kinds of performance measures, so this is also one, I need to give a measure, second I need to give an X measure. So generally I'll give false positives as the X measure and true positive. So if you see FPR, false positive rate, that is what I'm giving as a part of the X axis, and TPR, true positive rate, I am giving as the Y axis. So I can give these two things as the measure and X measure. So I'll create performance object, or I'll create a variable called performance, where I'm using a function called performance. I'll give pred, which is my prediction object. The measure I'll first give it, which is on the Y axis, I'll give it as TPR, which is my true positive rate, and X dot measure, which is on the X axis, I'll give it as FPR, false positive rate, I'll give as an input, and based on that I'll compute the perf. So if you look at the perf, it's an object of the class performance. X name is false positive rate, Y name is true positive rate. Again, there are some cutoffs that are being computed. Right, X values, it is doing these kind of cutoffs for the X values, and these are the corresponding Y values. So these are the ones that are typically plotted. On the X axis you see these kind of points. On the Y axis we are seeing these kind of points, and based on that the plotting is typically happening. So I can very well do the plotting of the performance. So I'll take the plot of performance, and probably let me set the color of it to be blue, and yeah, that should be fine. So we have got that this is my typical ROC curve. For this data set, this is my ROC curve, and I can also give a kind of AB line, right? A 45-degree line I can very well set. For this one, I'll create an AB line where I'm saying start from A equal to 0 and go to B equal to 1. So on one axis you take it as 0, the other axis you take it as 1, and probably you take the line type as dotted. For dotted I'll give the line type as 2. So this is how it is coming out. This is what is the AB line. So I'm able to create an ROC curve for my typical data. And the same way I can even compute my area under the curve. The area under the curve also can be computed from the performance itself. Probably let me show the performance itself. If you see here, there are a lot of optional arguments that are coming out, wherein measure wise, if you see here, I could have given the measure as AUC as well. If you see in the measures, I can directly give the AUC. I can give so many other measures as well, because performance is applicable for many kinds of performances. Under the ROC, I can very well look at computing the AUC by directly giving the measure as AUC. So I could have got performance underscore AUC. I would have simply called as performance, where I take the input as predicted, and the measure I can set it as AUC. Then it will directly give me the area under this AUC curve. So this is the curve altogether. So this is the area under this curve. So minimum it would be 50% because this is the area under the curve, but otherwise it should keep going up. So if you look at the perf underscore AUC, it tells me that it is approximately around 78.88%. The area under the curve is coming out to 78.88%. The more and more, now if you try comparing it with our table, so it's acceptable or fair at this moment, but yes, I want to improve this by trying out the various other measures. So I can very well compute the AUC, area under the curve, to finally make out whether this model is a much appropriate model or some other kind of a model altogether. Right? Then, so this is what I wanted to really look at when I'm talking about the performances. So these are the various things that we have already covered. If you have any further queries regarding the same, you can very well get in touch with me by giving me a call on the number that I have provided below, or you can send in an email at vamsidhar@facegurus.com. Thanks a lot for listening to this session. Thank you very much.